About a year ago, perhaps a little longer, I received one of these devices for repair. This is MaxiTPMS TS601 meter. It's used for communicating with the pressure sensors in your tires. You ever get those issues where the tire is fully inflated, but you get the symbol on the dash that the tire pressure is low? That's usually faulty or misconfigured sensor, and this device helps you diagnose it and perhaps even fix it. And especially when you replace those, you have to use this to basically configure it to work with your car. Now, last time I couldn't fix it, and now is my redemption, because now I know why. It's been over a year, my skills have improved, so now let's fix it. It's a very common issue on these. Hello friends, welcome back to the bench. Thank you very much for joining me. Our patient is our very much known TS601. What is the issue with it? Well, basically it doesn't work. The customer also checked the different battery, right? Swapped the battery in case it was the battery issue, and nothing, right? You click it and nothing happens, nothing on the screen. It doesn't turn on. So I already know what's wrong with it, but let's go through a typical diagnosis procedure. So first, what we want to see is we're going to connect it, we're going to give it 5 volts, and we're going to see how much current it draws. Right? I turn it on, it went up to like 90, now it's at around 40 milliamps. 40 milliamps. Now I'm going to position the battery over here, right? And I'm going to turn it on and plug in the battery. And if the current grows when you plug in the battery, which it does, and it drops when you disconnect the battery, that means our battery charging circuit is fine. Same thing we had on the previous one. Now, at this point, we could go further and analyze the board, how it works and stuff. You can see that in my previous video. The majority of what I said is correct, how the circuit works. However, I was wrong about the cause. Actually, I'm gonna show you. For this step, we need a thermal camera. I'm gonna use it without the macro lens. Next, it's pretty simple. Let's just position it like this so we can see it, right? And we turn it on, and there's a big bright spot over there. You see that? And it disappears when I turn it off. And I turn it on, there's a big bright spot, right? So something is shorted. Now the best case scenario is that the cup, the ceramic cup is shorted. Easy to identify, easy to replace, very cheap, very quick job. But it's never that simple. Ceramic cups will short out, but not in the devices like this. This is well protected. It's more common perhaps on laptops or electronics that have cups exposed. Because if you hit the cup, it shorts out. The chip in question is this one, right? The same chip that was on the other one. And in my previous video, I identified this one based on the markings. I don't remember what markings there were, but they were not the same. And the board is slightly different. The number of cups on the input is different. The layout is very similar, but there are some additional components. If you compare this image to the image from my previous video, you'll notice subtle differences, but overall it's the same design. So despite this being the same model, it is a little bit different inside. It's a further iteration, I assume, or maybe it's an older iteration, who knows. Usually with iterations you want to reduce the number of components, not increase, but in some cases you find that the number of components you had before is not sufficient and the next iteration adds them. So how do we find out what this chip is? Typically, you just Well, first you need to know the packages. It is very helpful if you know the packages. If you don't, you can take a picture, you can give it to ChatGPT or what have you, and it should be able to tell you exactly what the package is. There are subtle differences between certain packages, to the point where, to me, they look exactly the same, but for some reason they have different codes. I think maybe the height is a little different, or I don't know. But to me, they pretty much look the same, and if you search by the wrong package, you're not going to find the right chip. This package is SOT. We know that because it's a surface mount IC. This is SOT23-5. That 5 means that it's 1, 2, 3, 4, 5 legs on it, right? So with that, we can start looking for the chip. Now we see that it's BQ equals J1H. J1H, that will be the manufacturer markings. It probably describes when the chip was manufactured, maybe which production line, which machine, what process was used, what have you. This is only understood by the manufacturer. The equal sign, it's basically just a separator in this case. And what we're interested in is BQ, right? Now, this might be a little confusing because we do know about the BQ chips, right? But it's usually BQ and the 4-digit number. Those are the charger ICs that typically you find on laptops, and they are mainly responsible for charging the battery and actually enabling the main power rail. In this case, obviously, since this is SOT23-5, this is not going to be a BQ chip, obviously. So what we want to look for is SOT23-5 BQ. So let's Google it. And the Google immediately tells us that this is Texas Instruments REF 2030 QD whatever. This is not this chip. And how do I know? Well, I spent a little time analyzing it. So I know this is not the one, right? But we have plenty of results. And the first one from Mouser, we have power switch ICs, right? Is this going to be a power switch ID, or IC, sorry? Well, let's take a look. Let's take a wider angle here. And let's see from the power source, right? This is going to be our main power rail, our 5 volts. We have some larger, this is most likely some kind of linear regulator. It's attached to ground on the first pin. So maybe this isn't a power regulator, maybe it's just a transistor. This is ground. And we have big coil. And from the big coil, we have our chip over here, right? Now, we can start measuring all kinds of stuff over here, what makes connection to what, but it's going to be difficult because our pin number 2 is shorted to pin 3, 4, and 5. So everything is shorted here, that's why this chip is heating up. So we would have to remove it first before we do continuity checks. But let's ignore that for now, let's just focus on what we can see. We can see that we have plenty of caps around it. We have resistors, we have tiny cap and resistor over here. So this is going to be our configuration components. That's what's going to decide or configure this chip, what kind of voltage it delivers. And we have a coil. All right, this is something that I didn't notice or I didn't consider in my previous attempt on this very same device. And I identified this chip as a voltage detector, which also made sense, right? That the microcontroller has the voltage IC on it to reset it, or perhaps the memory, what have you. But if we get 5 volts over here, how are we supplying our Autel over here? This chip is going to have either 1.2 supply voltage or 1.8, 3.3 tops. It probably operates on 3.3, but no more than that. So if you supply 5 volts to this chip, it'll fry. It'll just go faulty. So the existence of this coil tells me that this delivers power to our logic over here. And what it does, it's going to be dropping, this is going to be a buck converter, it's going to be dropping from 5 volts to whatever we need. I think this is like 1.8 tops. I didn't check, but it's either 1.2, 1.8 volts, because this is the RAM memory. So most likely those two chips work on the same voltage, which will be much lower voltage than 5 volts. The coils over here are not necessarily for the use of the buck converter, although it could be. And that coil could be used by this chip to deliver power. The other possibility is that coil is just placed here to stabilize current. Just like capacitors stabilize voltage, inductors stabilize current. We also have another chip over here, but this one seems to be working fine. We have a lot of capacitance on the output. We have some transistors here. Another chip over here that doesn't seem to be a power chip. It could be some kind of EEPROM or something. Just something to initiate the rest of our digital logic over here. So to summarize, the existence of many capacitors and the coil right next to the chip tells us that it is a power chip. It's not going to be a voltage detector. It's not going to be a transistor or anything like that. It's going to be some kind of power IC. So let's scroll down a little bit. We can see that some come in a different package. This is SOT223, right? Also a very valuable piece of knowledge to know this package, because a lot of components come in this package, and they will also have 2-digit or 2-character alphanumeric code on them. So it's very useful to know the packages. And look here, what do we have? 10 pieces of BQ equals SOT23-5 new. And let's see the second picture, and look at that. It looks exactly like our chip. Now, as I said, those 3 characters over there, not 3 alphanumeric code, is just the manufacturer's code. We don't care about that. But we want to see BQ, and I don't think that equals even because it's always on all of those chips that you always have this equal sign over there. I've never seen any other than that. So I think it's just a separator, but I'm not sure. And the chip is RT8059GJ5. Now we could order it from eBay, but it's $315 on eBay with $8 shipping from China. So it's going to take a while, and the price is not that great. If we go to Mouser, we can see that the chip is around 30 cents. So we only pay about $2.20 for 10 of these. Plus, depending on which shipping you want, plus tax, it's close to maybe $15 for the whole thing. Let's see the data sheet. The general description is that this is high efficiency pulse width modulated step-down DC-DC converter capable of delivering 1 amp. And it can operate on 5.5 volts. So this checks out. The output voltage is anywhere from 0.6 to VN. Pin configuration. Our pin number 2, that is shorted to pin number 3, 4, and 5, is ground. So feedback and VN are shorted to ground. And also LX is shorted to ground. What is LX? LX is the external inductor. So this indeed does need an external inductor, which makes sense. And here we have few configurations. Depending on what inductor we use, we adjust the values of R1 and R2 and CFF. CFF, do we have CFF over here? It's hard to see on the board because it's pin 3 and 5 in between, which that this would be. I don't see it here per se, but again, I can really see on the board. Now with this, we could infer what the output voltage is. I think it's going to be 1.8, maybe 1.2. It's most likely not going to be 2.5. Most likely it'll be 1.2 for the microcontroller and the memory. But we don't really need that because we're not designing this device, we're just replacing the chip. So those resistors will stay here as long as we correctly matched the replacement, unlike last time. So now let's just confirm. So with the pinout, this is our enable pin. It's probably shorted to VN. It is not. We have 0.7.8 voltage drop on this. So there's probably a resistor. It could be this resistor. It isn't. Yes, so it's this resistor. So this resistor on which we are dropping, what's the drop here? Yeah, 0.7.8. This resistor connects VN and feedback, and we also have a capacitor to stabilize the voltage. This is our ground, so if we connect between here, oh come on, and voltage in, we have 0.26, so it's not a dead short. Let's see resistance. We have around 500 ohms, and we have 500 ohms everywhere. So on the coil, so between the ground and the coil, between the ground and the coil, we have 3 ohms. Okay, so what does that tell us? The internal MOSFET has shorted out. So it's not a VN issue. On our last one, the device was supplied with 12 volts instead of 5 volts. And this chip just fried up because 5.5 volts is its maximum allowed input voltage. But on this one, it doesn't seem so. So let's check one more thing. So the coil and the ground, let's catch the, well, actually we can do here. So ground and the coil, we have 3 ohms. So now the question is this chip the only shorted component? It is heating up, but if something is shorted on the output, this chip will heat up because that's its job. It's supposed to deliver current to the rest of the board. If we have a short on the output, then this chip is working extra hard to try to push that energy, that 1 amp, to the output, and it's heating up. It's normal. It probably shouldn't be heating up like this, especially since we're drawing only around 40 milliamps. That's 0.2 watts, 0.1, 0.2 watts. So how do we find out? Well, let's remove the chip from the circuit and see if the short is relieved. So we want to get rid of that 3 ohms between the LX and ground. So first, what I'm going to do, in my last video I removed the antenna so I don't melt it and all that kind of stuff, but this time I'm going to do something a little bit different. I have a lot better flux now than I did back then. It's my in-house flux. It's available on eBay. The link is in the description. So first I'm going to switch to 200 degrees roughly, and I'm going to heat it up a little bit. This 200 degrees shouldn't melt anything, but don't keep it for too long. Now when it's hot, I'm going to put a little bit of flux on it. 370 degrees on my iron, a T245 handle, and I just want to heat it up from this side, heat it up from this side, just so the solder starts flowing. Okay, it doesn't want to budge, so let's treat it with 380 degrees. It should be relatively easy to be removed now, but if it fused into the board, it will be a little tricky. Well, it doesn't seem like it fused to the board, Yeah, the last one we had was completely burned, so that one maybe was fused to the board a little bit, or fused with the board. Now let's wick it while it's hot. Now let's just wipe it. And before we measure, let's let the board cool down. Now without the chip, we see where the traces actually go. So this is our ground. So these are input caps. This is VN and this is ground. So these two caps are on the input. These caps appear to be on the output of the coil. So this is our output. So now let's measure between the ground and the output, and we still have 3 ohms. So that's not good. Our short has not been relieved. So what do we do now? So now we need to find what is giving us 3 ohms. 3 ohms is too low, way too low. Even considering that it consumes 1.2 volts. Let's calculate that. Well, on 3 ohms, 1.2 volt will give us 400 milliamps and roughly half a watt. So this is actually acceptable. Let's take a closer look at the chip. Was it actually shorted? So this is our ground. Let's mind the polarity because there might be a flyback diode. And now let's see, between the ground and VN, what do we have? Well, Autel. And between the ground and the output, we have Autel. So that means the chip most likely is heating up because of abnormal current draw. This is not confirmed yet, but let's keep digging then. So when we power on the device, now it grabs 6 or 7 milliamps. So if we check our VN, we should have 4.7. That's good. Now our output obviously is not going to have anything. There are some millivolts over there, but that's fine. When I checked the voltages before I removed the chip, I didn't have input voltage. It was very low, and output voltage was pretty much 0, which points to the chip actually being faulty. Okay, I say let's do a little experiment. So what I did, I soldered on 2 wires, one for ground and one for 1.2. We expect it's 1.2 volts. And I'm going to supply 5 volts, and I'm going to supply the voltage from the battery to this rail. That should enable our chip, and if it's working, the device probably should turn on. Now I'm not using fresh battery. This battery actually is considered dead, but it's still showing 0.8, 0.9 volts on the tester. If I connect it, if I actually check the voltage on it, that's a nominal voltage, 1.1, 1.2, right? Because fresh battery, AAA, is going to have 1.6 volts nominal, and when you load it, 1.5. So I'm going to try with slightly discharged battery. Now first I'm going to supply 5 volts, then I will supply the voltage from the battery, if I can actually pull it off. We got no change over there. The device is not turning on. I'm not sure if I have to hold the button or just press the button, but it's not charging, or it's not turning on. So now let's try this, so we can see how much current is actually being drawn. Let's drop the voltage to 1.2. Then let's grab a thermal camera and see if anything is turning on. Now in this case, what we want to see is probably the microcontroller to start slowly lighting up evenly, perhaps memory, maybe some passive components around it. What we don't want to see is a heat spot in any of the chips, especially the microcontroller, like a tiny dot that is heating up somewhere in the chip. That means the chip is fried. What is it that is... Something is lighting up and it's not a microcontroller or memory, which is a good sign, because something else might be shorted behind it, and perhaps our chip is indeed functioning, is just doing its job or trying to do its job, but there's just too much current draw. Let's see again. So we're grabbing 0.3 watts. It's a very bright spot next to... Oh, okay. Okay, let me record it and I'll show you guys. And the recording is going up in 3, 2, 1, and it started. Now, take a look here. This, you can't really see it, but this is our microcontroller. I'm not sure if I can position it so we can see under the camera, or maybe without the macro lens, that will be probably easier. This is our microcontroller over here. This square over here, right? So if we zoom in on it, it's roughly in the center of the camera now. Now when I turn it on, what do we see? We see a bright spot in the microcontroller, something we don't want to see. So the microcontroller is fried. That is the source of our 3 ohms. So the numbers made sense that 3 ohms is, because it's not over an amp, right? So it kind of makes sense that it would be 3 ohms, but it's never going to be a linear resistance like that. So this whole configuration might take 400, 500, maybe even 800 milliamps at 1.2 or whatever. But you're not going to see it with your multimeter that it's 3 ohms and it's just linearly taking that much current. That current is going to be taken once the MCU starts working, once it starts communicating with memory, once it starts doing its job. That's when it starts consuming. So the multimeter should not show us 3 ohms, even though the math makes sense that this is proper power consumption, but it shouldn't be this linear. So I conclude at the moment that our power IC is good, which is too bad because I already ordered them. It's just trying to supply the microcontroller, and microcontroller is dead. Now, can we replace the microcontroller? That's not an issue, but we don't have the binary to put into that microcontroller. And I doubt that the manufacturer makes those chips available for purchase. I will check. Actually, I'm going to check it right now. It's not looking good. And the majority of the how internals work on this device come from my video. So it's really disheartening when you're trying to find something out and all the knowledge that you can find is the knowledge that you reverse engineered, which means nobody knows. Nobody knows anything about this device. So here are the options. So naturally, this device can be connected via USB to the computer and you can perform firmware update. So what if we removed the MCU, replaced it with blank MCU, and connect it via USB and perform firmware update? This will not work because other than the memory that holds the firmware, there's also a bootloader, and that bootloader is also belongs to Autel. So the new blank chip is not going to have that bootloader. It will have a bootloader that Autel puts on them. So you can connect it to USB, UART, what have you, and so for the chip to be enumerated. But the Autel software will not detect it. It will not upgrade the firmware because the firmware doesn't exist. Also, when you perform firmware upgrades, the manufacturer's tool will first read the current firmware to see if you can actually upgrade. It'll read all kinds of information about the device, like version and all that kind of stuff. So even if we replace the chip itself, it will obviously not work. So the only option over here is to just use another device that is faulty, broken, whatever. And preferably the one that maybe there's something wrong with the antenna, maybe a broken screen, maybe, I don't know, faulty battery, but battery replacement on these is nothing too intricate, right? It's just simple lithium-ion battery glued over here. You can replace it with pretty much any battery as long as it matches 3.7 volts. This is 11 watt hour battery, 3000 milliamp hours. So this is one fault on these that I cannot fix, even no matter how much I can try, and I can't fix this one. This is a part donor, which is too bad because you don't really need any more parts from this. Again, unless you find one that does work but has cracked screen or something like that. So that is too bad. We're gonna have to call the customer and deliver bad news. This one's not gonna live, which is too bad because this is one of the really capable ones. It's a really nice device. It's really you can do a lot of stuff with it. It's really too bad because I thought that this would be my redemption, because now I know what the chip is, right? So if that chip was the problem, like in the other one, it would have been a nice redemption job. But at least now we have a definitive confirmation that it's the MCU that is faulty. Because in my last job fixing this, I was kind of guessing. I was kind of expecting that MCU probably is fried. Well, if you provide 12 volts, yeah, sure, it will most likely be fried. But we didn't check that. Now we have definitive confirmation that it's the MCU that is faulty and nothing other than that, which is weird because why would it fail, right? This isn't the problem of supplying 12 volts like we had in the last time. It seems like the MCU just decided to die on us. Well, you know what they say, you can't win them all. This one is no fix unless we find faulty one to build one working one from 2 or 3 faulty ones. But I couldn't find any on eBay or anywhere else where I could buy this faulty. I'm not sure what people do with these when they're faulty. Do they send them back to the factory or just toss them in the garbage? Which is really too bad, because it can still provide a lot of replacement parts. Alrighty, thank you guys very much for watching. I hope you enjoyed that, and I shall see you guys in the next one. Hopefully we'll fix something. Take care, guys.